Welcome back, Year 13. So this is the third and final video for you addressing your knowledge gaps that you asked us to look at again. And this is video 3, looking at eustatic and isostatic changes in sea level, the El Nino southern oscillations, drainage basins and storm hydrographs, and also physical and human factors in volcanic eruptions. So let's get started. Now, eustatic change, first of all. Remember, these are long-term changes in sea level over thousands of years. Okay, so this happens globally and it's due to changing the volume of seawater. It's caused by climate change primarily. Of course, remember, when water heats up and it gets warmer, there is thermal expansion taking place. So it's anthropogenic, it's human caused, but it's also caused by the Milankovitch cycles and natural change in climate. Decreasing water volume produces lower sea levels, but increasing water volume produces higher sea levels. Thermal expansion, for example, produces higher sea levels. Interglacial periods, such as today, where glaciers are melting, see a spike in eustatic change. There's rising meltwater trickling down from rivers and streams into seas, and that increases the volume of the water and also increases the temperature of the water as well. So sea levels rose by 21 centimeters between 1870 and 2010 as a result of this interglacial period. That is eustatic change. This all leads to what's called marine transgression, rising sea levels, flooding of lowland areas. And so the key thing to remember then for eustatic is this. There's a eustatic fall in sea level. That's glacial periods when ice is being created and water is evaporating and sea levels are falling. Eustatic rise in sea level temperature, as I've just explained, when there is an end of a glacial period, the ice sheets are melting, the water is going into the sea, the temperature is rising, thermal expansion takes place, and the sea level rises. So eustatic change overall then is about sea levels rising and falling due to glacial and interglacial periods and water temperature rising or falling. Now, isostatic change in sea level, again, is long term. It is about sea level change, but this is local land level change. This is due to land change, okay, not sea change. So rises in local land level can cause a fall in local sea level. And that's probably due to, for example, glacial adjustment or deposition or tectonics. A fall in local land level produces a rise in local sea level. So if the land is falling towards the sea is going to rise towards the land. Okay? This then means that what you get, in effect, because of the land changing, is sea level being higher on the land. So isostatic change is all about the land changing in a local place, causing the sea level to be higher at that place. That is all you need to know here. Okay, so El Nino southern oscillations, or ENSO. Now, there are 3 types. There's a normal year, an El Nino year, and a La Nina year. So here is a normal year in the Pacific Ocean. And what we have is the east coast of Australia and the west coast of America. So Peru and Australia. Okay. Now, normally, the warmer water is in the east coast of Australia. Okay, so that obviously produces lots of evaporation, and therefore you get rain forming on the east coast of Australia. The air that travels over towards the west coast of South America is dry, because it dries as it's rained, and there is dry conditions therefore in Peru. And we also have the idea that the trade winds are moving towards the west. Okay, so the average wind in this area in a normal year is moving towards the west, towards that warmer water. So that is all you need to know about a normal year. Now, in an El Nino year, conditions change. So again, we have Australia and South America. What's happened this time is the winds have changed. The trade winds have changed. The average wind in the area has changed. Just like, for example, in coasts with longshore drift, when the prevailing wind changes, the longshore drift wind direction also changes. So what happens here in an El Nino year is the wind shifts towards the east a bit more. So the warm water is actually in the center of the Pacific Ocean, as you can see. And that causes the rainfall to happen in the center of the Pacific Ocean mainly. Dry conditions then take place on the east coast of Australia. All right, so the east coast is dry in an El Nino year. The west coast of South America, however, receives some of the showers that the east coast used to receive in Australia. So the warmer waters are causing more rainfall and flooding in, for example, Peru. And that is all you need to know about an El Nino year. Again, it's about the change in wind direction, which moves the warmer water away from Australia towards South America, and that causes wetter weather in Peru and South. Now, in an La Nina year, apologies, in a La Nina year, we actually have what's basically a normal year, but much more intensified. So as you can see, the warm water is back over Australia again. Okay. But all of the winds here are much stronger in a La Nina year. So the trade winds are stronger. Unusually high air pressure in South America. So there's drought and very dry weather over a long period of time. There's very warm water at the east coast of Australia. So there's increased cloud formations, increased heavy rain and flooding. And that is all because the trade winds are moving more westward than usual and they are stronger. And also the water has moved more forcefully towards Australia and is warmer as well. So that is all you need to know about the ENSO cycles in a normal year, an El Nino year, and a La Nina year. Okay, very different now. Let's go on to the water cycle and talk about drainage basins and the physical factors that make up drainage basins. So there are 5. Climate mainly impacts the inputs into the drainage basin and what comes out of it, rainfall, for example. Changes in the type of precipitation or the amount of evaporation taking place. For soil, soil is very important because of the different flows that run through the system. For example, surface runoff. So the type of soil is important. And it also determines infiltration rates, the amount of water that can be infiltrated into the soil. The geology as well affects surface runoff. So certain types of geology impacts percolation and the ability of the water to percolate through the rock, and groundwater flow rates as well. And this also affects the soil formation in the area too. We have another physical factor of relief, which means the shape of the land. That also affects surface runoff rates. So obviously a more sloping landscape will see higher surface runoff. A less sloping landscape would see less sloping or less surface runoff. The relief also affects the amount of precipitation. Obviously, a mountainous area receives more rainfall than a flat land area. And as I said, the slope affects the runoff dramatically as well. And finally, for vegetation, that definitely also affects surface runoff. We know that the presence of plants and trees, the roots intercept rainfall and water, infiltrate it and transpire it. In other words, the roots use the water to grow the tree, and evapotranspiration takes place. So the vegetation also and the amount of coverage in the drainage basin is very important. So they are your 5 basic characteristics physically of a drainage basin. Now, the human factors that affect drainage basin follows. River management. How much has the river been managed? So the construction of reservoirs, use for domestic supply, irrigation, and so forth, all affects how much water is in the drainage basin and where the water flows to. We know from the previous slide that deforestation massively impacts a drainage basin and the amount of water in the system. So when we deforest, we reduce evapotranspiration rates, and we increase infiltration and surface runoff rate. There will be more water flooding the area with deforestation taking place. And then there are two types of changing land use that can impact a drainage basin. We've got agricultural. Obviously, this is all about farming. So changing from arable to pastoral farming or pastoral to arable farming. Either way, no matter what change there is from farm to crop, from animal to crop farming, what happens is the soil gets changed. There's increases in surface runoff and increases in infiltration rates as a result. And finally, for changing land use in terms of urbanization, we know that building, for example, using tarmac or tiled or concrete speeds up surface runoff, increases flooding, and that's why many towns and cities are prone to flooding, because there is little soil for the water to be absorbed into. So the main components affected by humans are evaporation, evapotranspiration, interception, infiltration in groundwater, and finally surface runoff. Now let's just then also think about the Amazon as an example of this. The Amazon is a place where obviously deforestation has taken place on a dramatic scale over the last 50 or 60 years. So what we've actually seen in the drainage basin cycle is a lowering of humidity, less precipitation, more surface runoff, more infiltration, more evaporation, less transpiration because there's less trees, and more soil erosion because the soil is exposed. So the Amazon is a good example of where human factors affecting a drainage basin takes place. You could use this example quite easily if you're asked to write about the impacts that humans have on drainage basins. Now, we also want to go over hydrographs. So I want you to take a couple of seconds, just look at the two types of hydrographs on screen. So we have a flashy hydrograph and a subdued hydrograph. Now, a flashy hydrograph will have discharge or amount of water flowing through the river that rises dramatically quite quickly. As you can see, there's a high peak discharge. A subdued hydrograph has a lower peak discharge. Now, remember on hydrographs, what we see is the amount of rainfall taking place and the peak rainfall. And we also have a lag time. The lag time is the difference between the peak rainfall and highest amount of water flowing through the river. Okay, so what we can see here on this flashy hydrograph is there's been a rainfall event or a storm event. And so the river discharge starts to rise. But actually, there is, let's say, a 24-hour period between peak rainfall and peak discharge. So it takes 24 hours for all of the water to drain down into the river. Because obviously, in a drainage basin, for example, all of the water has to flow through the soil, surface runoff might take place, and so on. Okay, so in a mountainous area, in a drainage basin, this may happen. And we get our peak discharge. We have our rising limb and our falling limb as well. Rising limb, obviously, is when discharge is rising. Falling limb is when discharge is falling. And we finally have base flow. Now, base flow is very simply what would have happened if this storm event did not take place. You don't need to worry about that too much because you're mainly going to be talking about peak discharge and peak rainfall in relation to drainage basins. And then finally, for the subdued hydrograph there, we can see it's very similar. It's just that peak discharge is much smaller. Okay? And this might be because of the different type of drainage basin. So a subdued hydrograph, you would actually find in places that are less urbanized. Okay? So in places where more water is infiltrated into the soil and absorbed, and it doesn't get to the river. Okay? So we have our peak rainfall here on the left again. It takes a long time for us to reach peak discharge. We can see there nearly 60 hours. And it doesn't go as high as a flashy hydrograph. So you'd mainly find a flashy hydrograph in an urbanized area or a place where it's has been built on. You'd mainly find a subdued hydrograph in an area that is more rural because there's more opportunity for the water to be infiltrated the landscape, so less of it gets to the river. Now, that is all you really need to know about hydrographs, but you need to be able to link them to drainage basins. And I've just explained some of the characteristics there that link as well. And the final thing in this video you were asked me to look at was hazards caused by volcanoes and human and physical factors. I'm not going to spend long going through this because this is quite easy. I'm just going to remind you of some of the basic things. So on screen now, I'm putting up a list of all of the hazards caused by volcanoes. And the P for primary and S for secondary impact. We have pyroclastic flow, ashfall, lava flow, gas eruption, lahars, and jokulholes. Now, all of these are hazards caused by volcanoes. Now, we have to think about where people live in relation to these. So if we're in a very rural area, okay, and there's not much civilization around for many miles, some of these won't affect people at all. Okay, now pyroclastic flow is quite strong and dangerous, so that could affect people even if they live miles away. Ashfall can affect people miles and miles away, but is not as serious a threat or as dangerous as pyroclastic flow is if you live near it. So they are just very simply the hazards caused by it. Now, you need to look at the human and physical factors involved in volcano or volcanic eruptions. So I've just got a summary here on screen for you about vulnerability and resilience in terms of geographical factors, both physical and human. So education, housing, healthcare, and income. They are 4 human factors that can massively affect how much a volcanic eruption impacts. If they're well educated, in good housing, have good healthcare, and have good incomes, generally that all means that it's a more developed nation, and generally that means the impact of a volcanic eruption would be lesser. That is definitely the case for your FE local case study in. Although remember also geographically, so physically, Iceland is very rural. And that also means that there are less physical and human impacts on Icelandic people. But we also have the idea of governance. Poor governance can lead to major problems with natural hazards like volcanic events. Now, even though Haiti is not a volcano, Haiti is obviously has earthquakes, and in 2010 there was an excellent example of poor governance in terms of volcanic or earthquake preparation. So you could use Haiti as an earthquake example if you're asked about earthquakes, but if you're asked about obviously volcanic events, you could use your Philippines case study and you could use also your Icelandic cases. Finally, there on the right, geographical factors. So population density, isolation and accessibility and degree of urbanization. The higher the urbanization, the greater the risk because there's more people. The higher the population density also, the greater the risk. A sparse population or a rural population is naturally less at risk. And isolated areas are actually generally more at risk in terms of recovery and rescue because if there are people there, they are harder to reach. So isolationism can be an issue in terms of accessibility. Finally, there's a lot of information that's just come on screen. These are all of your major case studies for tectonic hazards. I'm not going to go through this entire thing. You can look at my previous GeogPods for that. This is all on there. What I am going to point out very clearly to you is on the very right-hand side where it says vulnerability factors. So the last 3 columns here, inequality, governance, and geographical factors. This is very, very, very useful for looking at the human and physical factors in volcanic eruptions. Inequality is a human factor. Governance is also a human factor. Geographical factors are obviously physical factors. So you could use this list of things for these case studies on screen as physical and human factors involved in volcanic eruptions. So you can read through that yourself there. You've got all of the examples, and I've previously done this with you in the Tectonics GeogPod anyway. So that is the end of this video. I hope you've found the 3 videos on filling your knowledge gaps useful. Please do speak to me or Huckle if you need anything else. But that should keep you going now, and that should answer the questions you have. Thank you.